Troubleshooting compressor breaker tripping involves several steps. Firstly, check the compressor specifications. Ensure that the compressors are rated for the current draw specified on the circuit, which is 20 amps in this case. Secondly, measure the starting current. Use a clamp meter to measure the actual starting current of the compressors. If it exceeds 20 amps, the breakers will likely trip. Thirdly, inspect the motor wiring. Check that the motor leads are properly connected and securely tightened. Fourthly, consider a soft start. Install a soft start device that gradually increases the current to the compressor during startup, reducing the peak current draw. Fifthly, adjust pressure settings. Set the compressors to a lower operating pressure, which can reduce the load and current draw. It is important to never use 30 amp breakers on 20 amp circuits. This is a safety hazard and can lead to electrical fires. Possible causes for the breaker tripping include starting current overload, where the compressors may be drawing a higher current during startup than expected. Motor issues could also be a cause, where the motors may be faulty or damaged, causing excessive current draw. Improper wiring, such as faulty wiring or loose connections, can cause voltage drops and increase current draw. Undersized circuits can also lead to tripping under sustained use if the dedicated circuits are undersized for the load. For recommendations, always use 20 amp circuit breakers. Replace any 30 amp breakers with 20 amp breakers to ensure safe operation. Consider installing soft start devices to reduce starting current. Verify compressor ratings to check that the compressors are rated for the current draw being supplied. If the issue persists despite the troubleshooting steps, consult a qualified electrician to diagnose and resolve the problem. Some additional points to consider regarding electrical circuits and compressor operation include understanding ampacity. Ampacity refers to the current carrying capacity of a conductor, typically measured in amps. The National Electrical Code, or NEC, provides guidelines for determining the appropriate ampacity of conductors based on factors such as conductor size, insulation type, and ambient temperature. It is important to select conductors with adequate ampacity to prevent overheating and potential fire hazards. The overcurrent protection devices such as circuit breakers are designed to protect electrical circuits from overloads and short circuits. Circuit breakers are rated in amps and are designed to trip when the current exceeds their rated value. The selection of the appropriate circuit breaker size is crucial for ensuring both safety and proper operation of electrical equipment. The NEC provides guidelines for selecting overcurrent protection devices based on the ampacity of the conductors and the type of load being served. Voltage drop is the reduction in voltage that occurs along a conductor due to its impedance and the current flowing through it. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC provides guidelines for limiting voltage drop in electrical circuits. These guidelines typically recommend limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. Grounding is the process of connecting electrical equipment and systems to the earth. Grounding helps to minimize the risk of electric shock and provides a path for fault current to flow back to the source, causing the overcurrent protection device to trip. The NEC provides detailed requirements for grounding electrical systems. Bonding is the process of connecting metallic parts of electrical equipment and systems together to create a low impedance path for fault current. Bonding helps to minimize the risk of electric shock and prevents the buildup of static electricity. The NEC provides detailed requirements for bonding electrical systems. Electrical safety is paramount when working with electrical circuits and equipment. It is important to follow all applicable safety codes and standards, and to use appropriate personal protective equipment, or PPE, such as safety glasses and gloves. Always de-energize electrical circuits before working on them, and use a voltage tester to verify that the circuit is de-energized. The electrical permits and inspections are typically required for electrical installations and modifications. These permits and inspections help to ensure that the work is performed in accordance with applicable codes and standards and that the electrical system is safe and reliable. In this specific case of the compressors, several factors could contribute to the breaker tripping issue, as you mentioned, having already replaced the wiring and receptacles as well as the breakers. The first possibility is high starting current. Compressors typically draw a much higher current during startup than during normal operation. This is because the motor needs to overcome the inertia of the compressor components and build up pressure in the system. If the starting current is too high, it can trip the circuit breaker. The second possibility is low voltage. If the voltage at the compressor is too low, the motor will draw more current to compensate, which can also trip the circuit breaker. Low voltage can be caused by a number of factors, such as undersized wiring, excessive voltage drop, or a weak power supply. The third possibility is a faulty compressor motor. If the compressor motor is faulty, it may draw excessive current, which can trip the circuit breaker. Motor issues could include worn bearings or shorted windings. The fourth possibility is a faulty circuit breaker. Although you have already replaced the breakers, it is possible that one or more of the new breakers are also faulty. It is recommended to test the breakers to ensure that they are functioning properly. The fifth possibility is ambient temperature. High ambient temperatures can cause circuit breakers to trip at low current levels. If the compressors are located in a hot environment, this could be contributing to the problem. To further investigate the issue, consider the following steps. Use a clamp meter to measure the starting current of the compressors. This will help you determine if the starting current is too high. Measure the voltage at the compressor while it is running. This will help you determine if the voltage is too low. Inspect the compressor motor for signs of damage or wear. This could indicate a faulty motor. Test the circuit breakers to ensure that they are functioning properly. Use a temperature gun to measure the ambient temperature around the compressors. This will help you determine if high ambient temperatures are contributing to the problem. Check the wiring connections at the compressor and the circuit breaker panel. Loose or corroded connections can cause voltage drops and increased current draw. Ensure that the compressors are properly lubricated and maintained. This will help to reduce the load in the motor and prevent it from drawing excessive current. If you are unable to resolve the issue yourself, it is recommended to consult a qualified electrician. An electrician will be able to diagnose the problem and recommend the appropriate solution. It is worth reiterating that replacing a 20 amp breaker with a 30 amp breaker is not an acceptable solution, as it creates a fire hazard. The circuit wiring is only rated for 20 amps, and a 30 amp breaker will not protect the wiring from overheating and potentially causing a fire. In terms of the NEC requirements, several articles may be relevant to this situation. NEC Article 430 covers motors, motor circuits, and controllers. This article provides requirements for motor overcurrent protection, motor disconnecting means, and motor control circuits. NEC Article 440 covers air conditioning and refrigeration equipment. This article provides requirements for the installation and wiring of air conditioning and refrigeration equipment, including compressors. NEC Article 210 covers branch circuits. This article provides requirements for the installation and wiring of branch circuits, including the size and type of conductors, overcurrent protection, and grounding. NEC Article 250 covers grounding and bonding. This article provides requirements for grounding and bonding electrical systems, including the grounding of equipment and the bonding of metallic parts. Additionally, be sure to check local electrical codes for any additional requirements that may apply in the specific location. These codes may be more stringent than the NEC requirements. In addition to the troubleshooting steps mentioned previously, consider the following points when evaluating the compressor installation. Firstly, check the nameplate and the compressors. The nameplate will provide information about the compressor's voltage, current draw, and other important specifications. Compare this information to the circuit breaker rating and the wiring size to ensure that they are properly matched. Secondly, verify the wiring size. The wiring size must be adequate to carry the current drawn by the compressors. The NEC provides tables for determining the appropriate wiring size based on the ampacity of the circuit. Thirdly, inspect the circuit breaker panel. The circuit breaker panel should be in good condition and properly labeled. The breakers should be securely mounted and properly sized for the circuits they protect. Fourthly, check the voltage at the receptacle. The voltage at the receptacle should be within the acceptable range for the compressors. Low voltage can cause the compressors to draw more current and trip the breaker. Fifthly, consider the duty cycle of the compressors. If the compressors are running continuously or for extended periods of time, they may be overheating and drawing excessive current. You may need to provide additional ventilation or cooling to the compressors to prevent them from overheating. Sixthly, evaluate the ambient temperature. High ambient temperatures can cause the compressors to overheat and draw excessive current. You may need to provide additional ventilation or cooling to the compressors to prevent them from overheating. Seventhly, consider the type of circuit breaker. There are different types of circuit breakers, such as thermal magnetic breakers and electronic breakers. Thermal magnetic breakers are more common and are typically used for general purpose circuits. Electronic breakers are more sensitive and are often used for circuits that supply sensitive electronic equipment. If the compressors are tripping a thermal magnetic breaker, you may want to consider using an electronic breaker. Eighthly, check for loose connections. Loose connections can cause voltage drops and increased current draw, which can lead to breaker tripping. Check all wiring connections at the compressor, the receptacle, and the circuit breaker panel. Ninthly, evaluate the condition of the wiring. Old or damaged wiring can have increased resistance, which can cause voltage drops and increased current draw. If the wiring is old or damaged, it should be replaced. Tenthly, consider the use of a surge suppressor. A surge suppressor can help to protect the compressors from voltage surges, which can damage the motor and cause it to draw excessive current. 11thly, check for any other loads in the circuit. If there are other loads on the circuit, such as lights or other equipment, they may be contributing to the breaker tripping problem. Try disconnecting these other loads to see if the problem goes away. 12thly, evaluate the grounding system. A properly grounded system is essential for electrical safety and can also help to prevent breaker tripping. Check the grounding connections at the compressor, the receptacle, and the circuit breaker panel. 13thly, consider the use of a dedicated circuit. If the compressors are sharing a circuit with other equipment, it may be overloading the circuit. Consider installing a dedicated circuit for each compressor to ensure that they have adequate power. 14thly, check for any signs of corrosion. Corrosion can increase the resistance of wiring and connections, which can lead to voltage drops and increased current draw. Check all wiring connections and components for signs of corrosion. 15thly, evaluate the location of the compressors. If the compressors are located in a damp or humid environment, this can contribute to corrosion and electrical problems. Consider relocating the compressors to a drier environment. 16thly, check for any signs of rodent damage. Rodents can chew on wiring and insulation, which can cause shorts and other electrical problems. Inspect the wiring and components for any signs of rodent damage. 17thly, consider the age of the equipment. Older equipment may be more prone to electrical problems. If the compressors are old, you may want to consider replacing them with newer, more efficient models. Finally, as a general practice, any electrical work should be performed by a qualified electrician who is familiar with the NEC and local electrical codes. A qualified electrician will be able to properly diagnose and repair any electrical problems. When dealing with electrical systems, adherence to safety protocols is paramount. Firstly, always to energize the circuit before working on it. This can be achieved by turning off the circuit breaker that supplies power to the circuit. Use a voltage tester to verify that the circuit is de-energized before touching any wires or components. Secondly, use appropriate personal protective equipment such as safety glasses, gloves, and insulated tools. This will help to protect you from electric shock and other hazards. Thirdly, never work on electrical systems in wet or damp conditions. Water is a conductor of electricity, and working in wet conditions can significantly increase the risk of electric shock. Fourthly, be aware of your surroundings. Make sure that there are no exposed wires or other hazards in the work area. Keep children and pets away from the work area. Fifthly, follow the manufacturer's instructions. Always follow the manufacturer's instructions when installing or repairing electrical equipment. This will help to ensure that the equipment is installed and operated safely. Sixthly, know your limits. If you are not comfortable working on electrical systems, do not attempt to do so. Hire a qualified electrician to perform the work. Seventhly, use the right tools for the job. Use insulated tools that are specifically designed for working on electrical systems. Do not use tools that are damaged or worn. Eighthly, inspect your equipment regularly. Check your electrical cords, tools, and equipment regularly for signs of damage or wear. Replace any damaged or worn equipment immediately. Ninthly, be aware of the risks of arc flash. Arc flash is a dangerous electrical explosion that can occur when working on energized electrical equipment. Wear appropriate arc flash protection when working on energized equipment. Tenthly, follow lockout-tagout procedures. Lockout-tagout, or LOTO, procedures are used to ensure that electrical equipment is de-energized and cannot be accidentally energized while it is being worked on. Follow LOTO procedures whenever working on electrical equipment. The use of soft starters can have several benefits in compressor applications. Firstly, reduced inrush current. Soft starters gradually increase the voltage applied to the motor during startup, which reduces the inrush current. This can help to prevent voltage dips and reduce stress on the electrical system. Secondly, smoother acceleration. Soft starters provide a smoother acceleration than traditional across-the-line starting methods. This can help to reduce mechanical stress on the compressor and the driven equipment. Thirdly, adjustable starting parameters. Soft starters allow you to adjust the starting parameters, such as the starting voltage and the acceleration time. This allows you to optimize the starting performance for the specific application. Fourthly, improved motor protection. Soft starters can provide improved motor protection by monitoring the motor current and voltage and providing protection against overloads, undervoltage, and other faults. Fifthly, extended motor life. By reducing the stress on the motor during startup, soft starters can help to extend the motor life. Sixthly, reduced energy consumption. Soft starters can reduce energy consumption by optimizing the starting performance and reducing the amount of energy wasted during startup. Seventhly, reduce mechanical wear and tear. Soft starters can reduce mechanical wear and tear on the compressor and the driven equipment by providing a smoother acceleration and reducing the stress on the system. Eighthly, compatibility with different motor types. Soft starters are compatible with a wide range of motor types, including induction motors and synchronous motors. Ninthly, easy installation and configuration. Soft starters are typically easy to install and configure, with user-friendly interfaces and intuitive programming options. Tenthly, cost-effective solution. Soft starters can be a cost-effective solution for improving the starting performance of compressors and reducing energy consumption. The specific choice of a soft starter should be based on the motor's horsepower and voltage, the type of load, and the desired level of control. Ensure that the soft starter is properly sized and configured for the application. Proper grounding and bonding are critical for ensuring electrical safety and preventing equipment damage. Firstly, grounding provides a path for fault current to flow back to the source, causing the overcurrent protection device to trip and de-energize the circuit. This helps to protect people from electric shock and prevent equipment damage. Secondly, bonding connects metallic parts of electrical equipment together to create a low impedance path for fault current. This helps to minimize the risk of electric shock and prevents the buildup of static electricity. Thirdly, grounding and bonding help to reduce electrical noise and interference, which can improve the performance of sensitive electronic equipment. Fourthly, grounding and bonding help to prevent the buildup of static electricity, which can damage electronic components. Fifthly, grounding and bonding help to stabilize the voltage in electrical systems, which can improve the performance of equipment and reduce the risk of voltage dips and surges. To ensure proper grounding and bonding, follow these guidelines. Firstly, use the correct grounding and bonding conductors. The size and type of grounding and bonding conductors must be appropriate for the size of the electrical system and the amount of fault current that could flow. Secondly, connect all metallic parts of electrical equipment to the grounding system. This includes metal enclosures, conduit, and other metallic components. Thirdly, use approved grounding and bonding fittings. Use fittings that are specifically designed for grounding and bonding. These fittings are typically made of copper or aluminum and are designed to provide a low impedance connection. Fourthly, inspect grounding and bonding connections regularly. Check the grounding and bonding connections regularly to ensure that they are tight and free of corrosion. Fifthly, follow the NEC requirements for grounding and bonding. The NEC provides detailed requirements for grounding and bonding electrical systems. Ensure that you are familiar with these requirements and that you follow them carefully. Sixthly, use a ground fault circuit interrupter or GFCI for receptacles in damp or wet locations. GFCIs can help to prevent electrical shocks. Always follow the manufacturer's instructions and local electrical codes when installing and maintaining grounding and bonding systems. Proper grounding and bonding can significantly enhance the safety and reliability of electrical systems.